Well, it's better than nothing, right? Okay. So we're here. We got them all typed in. Do you guys need a minute still to finish typing? Now what I'm going to do is I'm going to look at my graph. So the easiest way to get the graph, or I shouldn't say necessarily the easiest, but I think the best way to go about us for starting is to press zoom and then pick Command 6 for zoom standard. That'll give us the XY axis where the X's and Y's are -10 and +10, the two ends of our graph. So my intersection appears to be somewhere over here. You guys agree with that when you look at the picture? Yeah? Okay. So to find that specific point of intersection, I'm going to press second and the trace button. Just like we did to find the maxes and mins, what command from this list sounds like the one that I need? Intersect. So I'll pick that command. And now the calculator is going to ask me 3 questions. It's going to ask me which 2 curves do I want to find the intersection of. So you notice my cursor is popped up on my graph. So right now, if I move left or right, I can see the cursor is on this line right now, the line on top. Well, that's one of the 2 lines I want to find the intersection of, so I'll press enter. And you'll notice that my cursor has now automatically been toggled down to the second line, the line on the lower one. So that's the other line I want to use, so I'll press enter. And then it asks for a guess. So you could move that cursor close to where the intersection is, but you don't have to do that. Wherever you're at is fine. So hit enter. And it tells us that intersection is at the point 7, -3. What do you guys think? Not so bad, right? The calculator can handle all of that for us. No big deal. What happens, though, if we have more than 2 variables? Can the calculator graph things in 3 dimensions? No. Can we graph anything in 4 dimensions? Or 5, or 6, or 7? So we need to continue with some algebraic methods. Although this graphical method is nice in 2 variables, that's where it ends. Right? It's not very feasible for us to graph things in 3 dimensions. You can do it, but it takes a little bit of skill, and it's beyond the scope of this class to where I'm worried about you graphing things in 3 dimensions. Your calculator can't handle that. And then there is not a way to graph things in 4 and 5 dimensions because we live in a 3-dimensional universe, at least with our current sensory system. The physicists in the room would argue about how many dimensions actually exist, but that's beyond the scope of this class also. Is everybody okay with that plan? So we're going to continue to develop some other algebraic methods. I'm going to start in 2-variable systems because it's much easier to kind of get the hang of these methods when there's not, 3 or 4 or 5 variables floating around for us. But keep in mind that anything we're doing here with 2 variables, you could solve by graphing. But once we move past 2 variables, graphing ceases to really be a feasible option for us. So the next method that we'll talk about is called substitution. So we're going to solve the same system now using substitution. Now the idea with substitution, what we're trying to do here, is I'm going to rewrite one of the 2 equations, it doesn't matter which one, so that one of the variables is isolated on one side. And then I'm going to use that equation to substitute into the other one, creating one equation with 1 variable in it. That's the goal. Okay? So if I look at these two equations and I look at the variables involved, which equation and which variable would be the best one to try to isolate? Yes. Perfect. So let's try to isolate the x in the second equation. Why did you choose that? Perfect. So when you get the x by itself, you don't have to do any division, and you know that you're not going to create any fractions, right? In general, it doesn't matter which variable you isolate, but you can make your life a lot easier if you choose so that you don't get as, choose to get the least number of fractions as you possibly can. Not that fractions are that hard to deal with, but it's more time consuming, and I have better things in my day to do than like grind through a bunch of fraction arithmetic, right? I'm sure you guys feel the same way. So we'll start by just subtracting 2y from both sides. Everybody good with that? Now what I can do is, using the first equation, I can replace the x in the first equation with 1 minus 2y, because I know that x is equal to 1 minus 2y. So I have 2, and then 1 minus 2y plus 3y is equal to 5. Does everybody see that? What we did there? Notice the equation that we have now includes only one kind of variable. We have only y's. This we can solve for directly. So I'll start by just distributing my 2 through. And then I'll combine like terms. Negative 4y plus 3y is negative 1y. And then I'll subtract 2 from both sides, and divide by negative 1 gives me negative 3 for y. Now that I have this answer, I can use this to solve for x. I can take this answer and plug it back into any of the equations I had before to solve for x. The equation that I would choose to use is this one, because the x is already isolated and I don't have to worry about any division going on. And I can see there that negative 1 minus a negative 6 is equal to 7. And so once again, I'm left with my solution, 7, negative 3. Do we feel okay doing that? Should feel pretty easy still, right? You may have even done some of this in your Algebra 1 class. It's not uncommon that you've done a little bit of system solving there. If you haven't, that's okay. I'm approaching this still as something that you're seeing for the first time, but I recognize that probably half or more of us have seen and done a little bit of this before. Maybe you remember, maybe you don't, but it's okay. The third method is elimination. So again, we're going to solve this same system. We'll solve it 3 different ways here by the time we're done. But it's nice, I wanted to do it this way because we know what the answer is. So each one of these methods, we can know that when we finish, we got the right answer because it's the same answer each time, right? Okay. So the idea with elimination is that we're going to add multiples of these equations together so that one of the two variables cancel out when we do that. So right now, if I tried to add these two equations together, I'd get 3x plus 5y is equal to 6, right? If I just add straight down, that's what I'd get. Can we see that? Notice there, nothing is canceled out, right? That's not what we want to have happen. So what I would do is first I would multiply one or both of these equations by some number or numbers, so that when we add them together, something will cancel out. So let's pick a variable that we're going to try to make cancel out. So if we're going to pick, let's say we start by trying to cancel the x's. Okay, it doesn't matter which variable you choose to cancel first. If I were to pick the x's, and let's call these equation A and equation B just so we have a way to talk about them. What would I do so that when I added these two equations together, they canceled out? What would I have to multiply one or both of them by? -2 to which equation? B. So I could do A plus -2 times B. Good. What if I wanted to try to cancel the y's? What would I have to do to cancel the y's?
Multiply A by 2, B by -3.
Excellent. Does it matter which one of those two I try to do as my first step? No, it does not. Now, if you had your choice, which one of those two would you do? I would do the x's because there's less multiplication that I have to do and less chance of me goofing something up, right? But it doesn't matter. They're both going to work the same way. But let's choose to do this one. Everybody okay there? So if I do that, there's my equation for A, and then -2 times B gives me this. Oops. Is everybody okay with that? Are you guys okay with my notation where I'm doing A plus -2B? We get what I'm saying there? When I do my eliminations, that's how I usually notate what it is that I'm doing, what equations I'm using, and what I'm changing. I think that helps going back if you were to look at this to know where things are coming from. But it's important we understand what I mean when I write those symbols down. And this is just a made-up Mr. Kulikism. Like, there's nothing fancy about what I'm doing here. It's not standard or anything. This is just what I find convenient way to, notate what it is that we did. Okay, so if we add down, we get all the x's cancel. We're left with 1y, or -1y, excuse me, and equals 3. Everybody's okay here? Yes, Joe.
I'm just confused. So when it says cancel first, are you saying like
Cancel x's first,
no,
or cancel y's first?
So it says 2a under cancel y's first.
Uh-huh.
Does that mean that you're doing like 3 times 2?
I'm doing the entire equation A multiplied by 2. So 2 times 2x, 2 times 3y, 2 times 5. And then -3b means I'm taking the entire equation 3 and multiplying, or equation b and multiplying that by -3. So -3 times x, -3 times 2y, and -3 times 1. Is that cool? You feel clear?
Yeah.
Okay. So now, once we've added a and -2b together, we're left with an equation with one variable that we can solve easily. If we divide both sides by -1, we get -3. And now I can take that solution and substitute it back into either of the previous equations to solve for x. So let's plug that into equation B. It doesn't really matter which one you chose. I chose equation B because the x had no coefficient on it, so when I do the division, I don't have to do any division to solve for it. Not that that makes a big difference, but, you know, it's one less thing I gotta do, right? So that gives me x minus 6 equals 1, and when I add the 6 over, I get x equals 7. So there's my solution. Do you guys feel okay doing that? Okay. A natural next question would be, what does it look like when we're doing these algebraic methods and we get like no solution or infinitely many solutions? Like, what the heck does that look like? Should we do some examples where that happens? Okay. So I'm going to call these equations A and B, just so that we have a way to talk about them. Take a moment and look at these two equations and see if you can tell which situation we're in just by inspection. Yes? Which means what situation would we be in? No solution, infinitely many solution, or one solution. This is the infinitely many. If you have the same line twice, they're going to overlap the entire time, right? Does that make sense? So right away, I would say if this is a quiz or a test and you make that observation and you explain to me exactly what you said, and then write so infinitely many solutions, you could stop. And I'd be fine with that. Let's keep going and pretend we didn't notice that, though, because again, under a stressful situation like a test or something, you might not notice that right away. Right? If possible. You're expecting something else to happen and you're not looking for that, and that's easy to miss. So let's do substitution first. And then we'll also do this using elimination. Calculator right now. Okay. So, which variable from which equation are we going to isolate? Does it matter? Here, either any way we choose, we're going to end up with some crummy fractions going on, right? So I'm just going to use equation A, and I'm just going to get x by itself. So I added the 2y over, and then I divided by 3. Everybody okay there? And I'm going to take that now and substitute it into B. So equation A becomes this, and I'm going to substitute that into B. Everybody okay with what I've done there? Now I have one equation with one variable. This we can solve. So we'll distribute that 6 through. And when we combine like terms, we'll notice that we're left with 10 equals 10. Is this a true statement? Yes. So this implies that we have infinitely many solutions. Now, does that mean that you can pick any x and any y and that's an answer? No, right? It has to be an equation on the line. So usually the way we like to do this is we like to write something that's called a like a parametric answer, where we use a parameter to describe how you would find a given solution. So what we'll do is we're just going to use this part to create our parameter. So that piece that's highlighted in green says that if you pick a value for y, you can find x by doing 2/3 times that value plus 5/3, right? That's what that equation is saying. Does everybody agree with that? So I'm going to use that then to create my parametric solution there. So because I have infinitely many choices for y, I get infinitely many ordered pairs, right? But not any ordered pair is a solution. It has to be of that form. So for example, if I pick y to be 1, then we get 7/3, 1 as a solution. Right? And each time I choose a different y, I'm going to get a different solution that's on that set of overlapping lines. Does that make sense? Okay. Let's do this same problem using elimination. Oops. I already forgot what the numbers were, so I'm going to repaste it. I was going to just make another column for the elimination next to it, but I wrote too big. Okay. Which variable do you want to eliminate first, x or y? It's about the same, right? Okay. Let's say we're going to eliminate the x's first. How are we going to do that? Yes. What's it? Yes, very good. That's okay. I knew what you meant, but it's one of those like I need to make sure that we're being specific. Everybody's good with that plan? Okay, so when I take -2 and I multiply it by a, -2 times 3x is -6x. -2 times 4, or sorry, -2 times -2y is positive 4y. And -2 times 5 is positive 5. B, we didn't do anything to. So when we add down, we get that everything cancels on both sides, and we're left with 0 equals 0. This again tells us infinitely many solutions. That's a true statement. Everybody okay with that? And if I want to give the parametric form, what I would do is I would take one of these two equations and solve for either variable. So let's say we solve to get the y by itself on this first equation, just to do something different than we did last time. So we'll subtract 3x and then divide by -2. So that means that x, we have our choice, and our y, we can find doing that. Just notice that this is still the same answer that we gave before. So let's say x is 7/3, because we know from before that 7/3, 1 is a solution on this line. So if I pick x to be 7/3, y should come out to be 1, right? So that becomes 7/2 minus 5/2, which is equal to 1. So those two parametric answers we gave were actually representing the same solution set. Even though they look different, they actually represented the same solution set. Are we okay there? Yes, Jane, right?
So, yeah. So when you have
I'm going to ask you for that solution also, or that answer as part of the solution. Yes. So depending on what the directions would be, some people may or may not ask you for that. I will ask you for that. Mostly because we do similar work with that idea in your trig and pre-calc course next year. So I want to get you a little bit of exposure to it now before then. Okay? All right. So the big takeaway, when we get something where it's just a true statement in the course of solving, either whether it's substitution or elimination, that's our indicator that we have infinitely many solutions. Okay with that? Good. Let's do another example, this time where no solution happens. Okay, so let's say we have the system 2x minus 6y equals 1, and then negative x plus 3y equals 2. So take a moment and look at this for a minute and see if you can tell why just by looking at this, we would know that we have no solution. Yes. Great. So I'm sorry, what is your name again? Sydney, thank you. what Sydney's saying is if I take -2 times the left-hand side of b, that is equal to the left-hand side of a, but -2 times the right-hand side of a, or of b, excuse me, is not equal to the right-hand side of a. RHS is just right-hand side, left-hand side. Perfect. That's exactly right. And right away, if you see this, you can say no solution. And you can be done. There's nothing more to do here. There's no parametric answer to also include with this. No solution is no solution. You can be done at that point. But that's easy to miss, especially in a pressure situation where maybe you're taking a test. It's easy not to notice that. So let's continue doing this and see what happens so we know what to look for. If we just dive right into solving, because it's easy to do that. I want to do this. So let's say we're going to do substitution here. Okay. Which variable would you want to solve for? For the substitution, what's going to make the easiest variable to isolate? Sydney. Very good. I agree. So to do that, we'll subtract 3y and then divide by -1. And then we're going to plug that into a, excuse me. So that's 2 times 3y minus 2 minus 6y equal to 1. So again, this is my value for x that I've plugged into a. And when I distribute the 2 through, I get that. The 6y and -6y cancel. And I get that -1 or -4 is equal to 3. Or I'm sorry, is equal to 1. Is that true? No. So that's our indicator that this is no solution. If you get a nonsense answer, like 5 is equal to 8, or 0 is equal to 1, or whatever, that tells you no solution, and you're done. Is everybody okay with that idea? If we did elimination, as Sydney suggested earlier, we're going to do equation A plus -2 times equation B. So equation A was 2x minus 6y equals 1. -2 times B then would be -2x plus 6y is equal to -4. Oh, sorry. Yeah, -4, right? Yeah. So when we add down, we get 0 equals -3. And that's a bunch of hot garbage, right? Again, that's not true. So we can conclude no solution. What do you guys think? Yeah? So far, so good? Okay. This feels like a good place to stop. Don't you guys agree? Okay. So let's see, what can we do homework-wise? Okay, definitely can do homework 1 for chapter 3. And I'm not sure if I did this out of order. Yeah, I did do that. That's fine. And there's this one. Kulik? That's okay.
I'm confused on graphing, like, is the graphing for the substitution and elimination just like 3 different ways? Like, why can't you just always do graphing?
So the idea there is if we move this, if we extend this idea to 3 variables, graphing in 3 dimensions is not something your calculator handles and is pretty difficult to do by hand. And if you extend it to 4 variables, you can't even do that by hand. So we need an algebraic method to handle those situations. So we're developing those methods in 2 variables with the plan to extend this to 3 variable, 4 variable, etc. later. So we're just starting. Yes, you could do all these problems that we did with substitution and elimination by graphing today, but we won't be able to do that next time when we talk about a 3 variable situation. But rather than starting in the much harder, like there's more steps kind of to deal with because you have a 3rd variable. Rather than starting there to teach those methods, I like to start with the 2 variable to teach those methods and then extend it out to 3 variable. But that's what's going on. Does that feel okay? Okie doke. So for Sunday's homework check, you have homework 1, which is just some graphing stuff. That again, that's something where you'll answer some questions. And for problem 6, you can do this all on your calculator. So these ones here, they're just do on your calculator. There's one I ask you to do by hand just so that you can say you've done one by hand. And then homework 3 has 4 substitution problems and 4 elimination problems. Okie doke. So not too much stuff to do, right? And you have 20 minutes or 15 minutes or something here to get crack-a-lack, and you could probably knock one of these sheets out before you leave today. You know what I mean, guys? And let me just sync real quick because I just added those in there, just in case.